Welcome everybody for the last day of our Geometry and Physics session. Next speaker is Carlos Augusto Bassani Varea from Universidade Tecnológica Federal do Paraná, whose talk is titled Invariant Complex Direct Structures on Flag Manifolds. Thanks for being here, Carlos. You can start.
Thank you, Bruno. I would like to thank all the organizers for the invitation. It's a pleasure to be here today presenting this work. This is a joint work with Cristian Ortiz from USP. This is a work that we are still doing. We are finishing this work. And I divided the presentation in the following way. So I will start presenting some preliminary concepts about generalized geometry. Then I will talk, actually I will just define the notion of flag manifolds. And then I will talk about invariant generalized complex structures on flag manifolds, which is a particular case of the invariant complex direct structures on flag manifolds, okay? So the notion of direct structures were introduced by Kuhan in this paper. And now today we know this direct structure as part of we know as generalized geometry. And inside the generalized geometry, the generalized complex geometry is the most studied area. This notion of generalized complex geometry were introduced by Hitchin, initially studied by his students Marco Gualtieri and Gil Cavalcanti. And one of the advantages of studying this generalized complex structure is that we can study complex and symplectic geometry inside in the same framework. Okay, so let's start defining these notions on vector space, and then we can extend the notion for smooth manifolds. So let's consider V a vector space and denote by V star its dual. So the space where generalized geometry lives is on the space plus its dual. Okay, so the space that we are going to work today is the space, the direct sum of the space with its dual. And in this space, we have this form defined, naturally defined in this way. We have a vectorial part and a form, and we apply in this way. And we define a direct structure on a vector space V as a Lagrangian subspace on V plus V star satisfying with respect to this form here. And when we say Lagrangian subspace, we mean maximal isotropic subspace. Okay. And the basic examples of direct structure are the space V and the dual. They are trivially satisfy the condition of being a Lagrangian subspace here. We also have this another example. If we consider a subspace E, then we consider E plus its annihilator. So you can check directly that this is a direct structure on B. And a little more sophisticated example is the third one, where we consider a subspace E and the form epsilon. And then we can define the subspace L of E epsilon in this way here. And we can prove that this is a direct structure. Okay, this is an important example because one can prove that actually every direct structure on a vector space V is of the form L E epsilon for some E and epsilon. Okay, so if you have a direct structure, you can find a subspace E and a two-form L epsilon, such that this direct structure is of this form here. And we can extend this notion to the complexification of the space V plus V star. And then we can define what is a complex direct structure, which is a Lagrangian subspace in the complexification of this space. And this is the notion of complex direct structure that we are going to work here. Okay. As I mentioned in the beginning, the notion of generalized complex structure is a particular case of a Dirac structure. So in order to recover this definition, we need the definition of the real index. Okay. So the real index of a vector space is the complex dimension of the space with intersection with its conjugate. So the real index of a Dirac structure will be defined in this way here. Okay, so let me define, let me give you the usual definition of generalized complex structure, and then I will explain how to recover how to see it as a Dirac structure, a particular case of a Dirac structure. So a generalized complex structure is an endomorphism on the space V plus V star, satisfying two conditions: a complex condition, it means that J square is -1, and a complex condition, and a symplectic condition here. Okay. And the first example, maybe the only example that you find on the literature, are these ones. If we have a complex structure on V, which means an endomorphism on V satisfying the J square is -1, then we can construct a generalized complex structure in this way here, putting -J and J star here. Okay, and you can check directly that it satisfies these two conditions here. And in the same way, if we have a symplectic structure on V, then we can define a generalized complex structure associated to omega in this way here. Okay, and one advantage of working on flag manifolds is that I made a lot of examples explicitly. Okay, we will see this in this talk. And this is the proposition that relate generalized complex structure with Dirac structures. Okay, so this proposition is saying that a generalized complex structure is a Dirac structure satisfying this condition here, which means that is a Dirac structure with real index 0. Okay, so a generalized complex structure is a Dirac structure with real index 0. So a generalized complex structure is a particular case of Dirac structure. And as I said, we can extend the notion from vector space to a smooth manifold, but when we pass from this setting of vector space to smooth manifolds, we need the notion of the Coulomb bracket, which is defined by this expression here, where on the right-hand side, we have the Lie bracket, and this L is the Lie derivative. Okay, so we define a complex Dirac structure on a manifold M as a Lagrangian subbundle on the complexification of the direct sum of the tangent plus the cotangent bundle of the manifold, which is involutive with respect to this Coulomb bracket. Okay, in the same way, we can extend the notion of generalized complex structure, and thanks to that proposition that relate the generalized complex structure with the Dirac structure, we have two ways to look at the definition of the generalized complex structure. Okay, actually, we put the almost here because when we pass from vector space to smooth manifolds, we need some kind of integrability. Okay, so in a first moment, it's a generalized almost complex structure. We can see in two ways. We can see it as an almost complex structure on the tangent plus the cotangent bundle, which is orthogonal with respect to the natural bilinear form that we defined in the beginning of the talk. Or we can see it as a maximal isotropic subbundle on the complexification of the tangent plus the cotangent bundle, satisfying the condition that have real index 0. Okay, so we can see one generalized complex structure in one of these two ways. Actually, we have a third option, which is by means of the pure spinor, but we are not going to enter in details in this definition here. Okay, this two is enough for us. As I said, when we are working on manifold, we need a condition of integrability. So we are going to say that a generalized almost complex structure is integrable when its eigenbundle is Courant involutive. Okay, and we can say that this is a good notion of integrability because it agrees or it extends the notion of integrability that we already have in complex and symplectic geometry. I mean, if we consider the generalized complex structure that comes from a complex structure, then it will be integrable if and only if the complex structure is integral in the usual sense, if the Nyhan-House operator is zero, Nyhan-House tensor is zero, okay? And the same happens here. Omega, J omega will be integrable if and only if omega is closed, which means that omega is actually a symplectic form. Okay, so the notion of integrability for generalized complex structure, it extends the notion, it agrees with the notion of integrability that we already have in complex and symplectic geometries. Another way to look at the integrability of generalized complex structure is by means of the Nyhan-House operator, which is defined by this expression here, where on the right-hand side, we have here the bilinear form defined in the beginning of the talk, and this is the Courant bracket, okay? So we are going to say that J, a generalized complex structure, is integrable if and only if the Nyhan-House operator is zero when we restrict it to the eigenbundle of J. Okay, this is an equivalence that we are going to use in this talk to analyze the integrability of the generalized complex structure. Okay, so now I'm going to talk a little about flag manifold. I'm going to fix some notation and give you the definition of flag manifold that we are going to use here. Okay, so it's a lot of data here. So we are going to consider a semi-simple Lie group G. It's Lie algebra G. H will be a Cartan subalgebra. Then we have the root space decomposition of the Lie algebra in this way here. We can define elements H alpha, which is defined by this expression here, where here is the Killing form of the Lie algebra. Okay, this bracket here. Then we can define HR by this way. Okay, we are going to fix a Weyl basis, which are a basis where the elements satisfy these conditions here. By pi plus, we are going to denote the set of positive roots of the Lie algebra, and by sigma, we are going to denote the simple root system. Okay, so we can define the Borel subalgebra as the Cartan subalgebra plus the root space associated to the positive roots, like this. And a subalgebra P is parabolic when it contains the Borel subalgebra. Okay, all of this because the definition of flag manifold is the following one. A flag manifold is a homogeneous space, G over P, where P is the normalizer of a parabolic subalgebra. Okay, but today I'm going to talk only of maximal flag manifold, and it occurs exactly when the parabolic subalgebra coincides with the Borel subalgebra. Okay, so from now on, when I say a flag manifold, I mean a maximal flag manifold. Okay, but to do computations with flag manifold, it's easier if we look into a compact real form. Okay, so we have another way to look at the flag manifold, and it's by means of a compact real form. Okay, so we define U, we consider U a compact real form of the Lie algebra G, which is defined by these guys here, where A alpha and S alpha are these elements which are defined in terms of the Weyl basis. Okay, so we can prove that the flag manifold can be written as U, which is the Lie group associated to the Lie algebra U, over T, where T is actually a maximal torus on U. If we consider a partial flag manifold, not a maximal, we change only here is not necessarily a torus, but it will be a centralizer of a torus. Okay, but for us today, as I said, it's going to be a maximal flag manifold, so it's U over T, where T is a maximal torus. Okay, and the tangent space of the flag manifold we are going to denote by M. Okay, so for flag manifolds, the study of complex structure is it's all well known, and it goes back to Borel. He proved that an invariant almost complex structure on a flag manifold can be described by this way here. Basically, it's described by its signs. In some papers, you will find that J is equal to the sign. The denotation is just the signs. He also proved that the integrability of a complex structure, an invariant complex structure, depends on triple of roots satisfying this condition, that alpha plus beta plus gamma is equals to 0. Okay, we also have this proposition here that says that if J is integrable, then the set of roots such that the sign is positive in the complex structure, it defines, it's a choice of positive roots for the root system of the Lie algebra. Okay, so motivated by these results from Borel, in my PhD, Professor Luis San Martin, which was my advisor, he proposed to try to find something close to this, extend these results in the case of invariant generalized complex structures on flag manifolds. Okay, so this is what I'm going to talk about now. And when we say invariant, we mean invariant under the isotropy representation. But since we can see the flag manifold as a compact Lie group, okay, is a homogeneous space where the part above is compact, then the flag manifolds are reductive homogeneous space. It means that we can identify the isotropy representation with the adjoint representation, which is easier to work. It's well known. And also the invariance guarantees that we can reduce the problem to the origin. Okay, so instead of working with structures on the tangent plus the cotangent bundle, we are going to work with structures on the tangent space at the origin plus the cotangent space at the origin. Okay, and M denotes the tangent space at the origin of the flag manifold. Okay, so we can prove that any subspace on the tangent plus the cotangent space at the origin can be decomposed in terms of the root spaces. Okay, and its duals. And we prove it that actually this space L is maximal isotropic if and only if each part of on the right hand side here that we call L alpha is maximal isotropic inside U alpha plus U alpha star. Okay, so we reduce our problem of studying on the tangent plus the cotangent bundle to study the problem in the tangent space at the origin plus the cotangent space at the origin. And now we are reducing our problem of studying all the tangent space at the origin to study only on each root space U alpha plus U alpha star. It means that an invariant generalized complex structure on a flag manifold can be decomposed in blocks in the diagonal, as we have here, where each of these blocks is an invariant complex structure on U alpha plus U alpha star. Okay, so basically we reduce our problem of studying endomorphisms J alphas on a 4-dimensional space, satisfying these 3 conditions here, that J is a complex structure, J square is -1, J is orthogonal with respect to this bilinear form, that actually we can prove that bilinear form defined in the beginning of the talk. In the case of flag manifold, it coincides with the Killing form of the Lie algebra, and we are asking that to be invariant under the isotropy representation, which is the adjoint representation in our case. Okay, so you can take a four-dimensional matrix and start to do computation and demand to satisfy these three conditions here. And after doing all these computations, you can conclude that there are only two types of matrices satisfying all these properties, plus or minus this matrix here, or this other matrix J alpha satisfying this condition here. Okay, so basically what we have is the following. An invariant generalized almost complex structure on a flag manifold it will be blocks on the diagonal where each of these blocks is either of complex type or else non-complex type. Okay, I call this complex type because it comes from a complex structure. If you remember the first example that I gave of generalized complex structure, we have here a generalized complex structure that comes from a complex structure. It's minus J and J star here. And the other is called non-complex type because it does not come from a complex structure, okay? But later, I proved it together with Fabricio Valencia and Elizabeth Gasparin that actually the second case here is a B-transformation of a simplex type structure. Okay, so basically we have up to B transformations, we have only complex type and simplex type structures here. Okay, so if you want to describe a generalized complex structure and almost complex structure on a flag manifold, you just take a flag manifold and you start to put these blocks, complex or non-complex type, in the diagonal any way you want. Okay, but now the question is, which of these structures are integrable? Okay, so to analyze the integrability, we use the Nyhan-House operator, and we can prove in a similar way as Borel proved that the integrability depends on triple of roots of the type alpha, beta, and alpha plus beta. Okay, and the Nyhan-House operator will be 0 when we have triple of roots of this type, alpha, beta, and alpha plus beta, and the associated complex structures J alpha, J beta, and J alpha plus beta must still be one of these rows in this table, okay, where the last row must satisfy this algebraic condition here. So if you have an invariant generalized almost complex structure on a flag manifold and you want to know if it is integrable or not, then you need to take every triple roots of the type alpha, beta, and alpha plus beta and see if it fits in one of these rows of the table. Okay, trying to get a better way to look at this integrability, we start to do another things, and we prove it together with Professor San Martin, my PhD, this lemma, that generalized lemma from Borel, that says that an invariant generalized complex structure, I put here integrable to emphasize that the structure need to be integrable. If you have J in this way, then the set of roots such that we are choosing the positive structure associated to the complex structure and the roots associated to the non-complex type with X alpha positive, then it will be a choice of positive roots. Why this extend the result from Borel? Because when we have an invariant generalized complex structure that comes from a complex structure, then this second row does not exist. Then we have only the first row, and we are choosing the roots such that the sign is positive of the complex type structure. Okay, so we extend that result. And using this lemma, we can prove the following one, that an invariant complex structure, an invariant generalized complex structure, if we have J, an invariant generalized complex structure, then there exists a simple root system and a subset theta of sigma, such that J alpha is of non-complex type for the roots in the generated by theta. The generated by theta is in the following sense. If alpha and beta are roots on theta, then alpha plus beta will be in the generator. Okay, and J alpha is of non-complex type, then J alpha, then the root is outside the generated by theta. So basically we're separating the case where, so we have an invariant generalized complex structure, then the non-complex type is here and the complex type is here. We can do this. And reciprocally, we proved that given a simple root system and a subset of sigma, then we can construct an invariant generalized complex structure satisfying these conditions here. That is complex of non-complex type inside the generated by theta and of complex type outside there. Okay, so this completely describe all invariant generalized complex structure on flag manifolds. Okay, this was my work on my PhD thesis. And in 2020, I was working with Christian Ortiz in a postdoctoral position, and he proposed it to me to study invariant complex Dirac structures on flag manifolds. There is a work from the thesis of Dan Agüero from INPA. He studied invariant complex Dirac structures with constant real index. And Christian was part of the jury, and he proposed me to try to extend my PhD results to this setting of invariant complex Dirac structures. So the idea was try to describe them. So again, we are going to work with invariant structures. So invariant means invariant by under the isotropy representation, which coincides with the adjoint representation in our case. Okay. And again, the invariance will guarantee that we can study only at the origin. But now, in the case of complex Dirac structure, we don't have the condition of real index 0, because we are going to study what happened with positive real index. Okay, and when we don't have this condition here, we lost the notion of endomorphism, so we can not work with matrices. Okay, but that proposition that says that we can decompose the subspace in terms of the root space still work. So basically, for our purpose, we can reduce the problem of studying invariant complex Dirac structures to study invariant complex Dirac structure on each root space U alpha plus U alpha star. Okay, the complexification, because we are studying complex Dirac structures. Okay. Okay, so again, we want to study the invariant complex Dirac structures on flag manifold. So basically what we need to find is the subspaces L alpha on U alpha plus U alpha star, the complexification of U alpha plus U alpha star, satisfying the condition that L alpha is maximal isotropic, L alpha is invariant under the adjoint representation, and the whole structure L must to be involutive with respect to the Coulomb bracket. Okay. Okay, so if we take a two-dimensional subspace and demand it to be isotropic, then we get only 6 possibilities, which are this one here. But when we demand to be invariant, we see that item 3 and 4 is not invariant. So when the maximal isotropic subspace, which are invariant under the isotropy representation, are these 4 here. And the third subspace here must satisfy that B1 over A1 is plus or minus I. So if we rewrite the subspace L alpha, we recover this guy here. So basically, before analyze the involutivity, let's see what we have. So items 1 and 2 are the root space U alpha, or the dual of the root space of U alpha, and they have real index 2. Item 3 can be rewritten of this way, and this is exactly the I eigenspace of a generalized complex structure of complex type. So it will have real index 0 because a generalized complex structure is a Dirac structure with real index 0. Okay, so remains the case 4. And the case 4, we can separate in two cases when B1 over A1 is real or not. If it's real, we can prove that it has real index 2. If not, we can prove that it has real index 0. So if it has real index 0, it comes from a generalized complex structure, and we can prove that it actually coincides with the I eigenspace of a generalized complex structure of non-complex type. So we recover the two possibilities of generalized complex structure here. So summarizing what we have, the invariant maximal isotropic subspace L alpha are the root space U alpha, its dual, the I eigenspace of a generalized complex structure of complex type here. I think 5 is the I eigenspace of the generalized complex structure of non-complex type, and this new guy here, number 4. Okay, so these are the only possibilities. So now we proceed to analyze the involutivity of these structures. And we are going to use the same idea, and we can prove that L is Courant involutive if and only if the Nyhan-House operator vanishes when we restrict it to L. Again, we can prove that the involutivity will depend on the triples of roots of the type alpha, beta, and alpha plus beta. Okay, so to make the notation easy, we are going to denote the subspace by its item. So subspace of this type, we are going to call 1, type 2, type 3, type 4, and so on. Okay, so if we have a triple of subspace L alpha beta and L alpha plus beta in this way here, then we are denote this triple by 1, 2, 4. Okay, just to make the notation easier. Okay, so a triple of subspace of invariant Dirac structures L alpha, L beta, and L alpha plus beta can be of real index 0, 2, 4, or 6, because we saw that each of these subspace have real index 0 or real index 2. Okay, so it can be 0, 2, 4, or 6. And then I'm going to analyze the involutivity according to the real index. Okay, so if it have real index 0, then we have these possibilities. All of them of type 3, 2 of type 3, 1 type 4, all of type 5. And the involutivity conditions are given in terms of the signs for the complex type and this other condition here. And this table of real index 0 recover exactly the table of integrability in the case of generalized complex structure that I presented here. And you can see that this condition here for the last row is exactly the same condition that we have here for the last row. Okay, so real index 0, it comes from complex structure, generalized complex structure, so we recover the integrability of generalized complex structure here. Okay, for case 2, for real index 2, we have a lot of cases, and the involutivity conditions are given in this slide here. For real index 4, we have some cases, and for real index 6, we have these cases here. Okay, so what we can conclude from this, so this are all the possible cases for involutive complex Dirac structures on flag manifolds. So you take a Dirac structure, an invariant complex Dirac structure on a flag manifold, then it must satisfy these tables here. So what we proved, this is a paper with Cristiano Ortiz that we're still finishing. I think in the next month or 2 months from now, we can upload it on archive. But we proved that an invariant complex Dirac structure on a flag manifold, it has constant real index, and the real index is equal to 2k, where k can vary between 0 and the number of positive roots. Okay, it's actually a immediate consequence of this proposition that you can find on Danagüero's thesis that says that if you have a complex Dirac structure with real index r, then it must exist a natural number m satisfying this condition. Since the flag manifold is always even dimension, then it's quite immediately. But we saw that the possibilities of the Dirac structure here have real index 0 or real index 2. So it's consequence of this. But more than that, we proved that given a semi-simple Lie algebra G, and consider the maximal flag manifold associated to this Lie algebra, we proved that for every k, we can construct an invariant complex Dirac structure with constant real index equal to 2k. Okay, so you have L positive roots. You can choose nk between 0 and L. Then we proved that we can construct an invariant complex Dirac structure with that real index 2k. Okay, just to do an example here before finishing. This is the simplest example. We consider the Lie algebra SL2, so we have only one positive root that we call alpha. The flag manifold associated to G is, you can identify it with the projective space P1. And since we have only one positive root, then we can have only invariant complex Dirac structure of real index 0 or real index 2. Okay, so with real index 0, if we consider L alpha the invariant complex Dirac structure, then we know an invariant complex Dirac structure with real index 0, it comes from a generalized complex structure. So it can be of complex or non-complex type. Okay, and as I mentioned before, we proved it together with Gasparin in Valencia that the generalized complex structure of non-complex type is actually a B transformation of a simplex type structure. So basically, in this flag manifold, we have only invariant complex Dirac structure with real index 0, structures that comes from complex or simplex structure. Okay, and the real index 2, we have 3 possibilities. Remember that is the root space associated to alpha, that in this case is the tangent space at the origin, because we have only one root, the cotangent space, or the dual of the root space, and the other guy that appeared here. But we proved I proved with Cristiano Ortiz that actually this third guy here is actually a B transformation of the first type of this guy here, of the tangent space at the origin. So up to B transformations, we have only the tangent space or the cotangent space at the origin. And this is general. Actually, we proved that this L alpha here is a B transformation of this L alpha here. So when we have, In this case here, type 4 is a bit transformation of type 1. So up to bit transformations, we have only 4 invariant complex digit structure. So we are still finishing the paper, but for real index 2, if we consider the invariant complex digit structure with constant real index equals 2, we have a good description, and it's quite similar to the case of the generalized complex structure. We can define a set where we are choosing a positive is a choice of positive roots, and then we can separate the digit structure inside the subset theta in the same way that we have on these two theorems. For real index 2, we have a similar theorem that proved that we can separate the case of real index 0 for one side and real index 2 for the other side. And I think that's it. Thank you.
Thanks for your talks, Carlos. Does anyone have a question or comment? If not, Carlos, thank you very much for presenting our session.
Thank you, Bruno, for the invitation.
Thanks.
Stop sharing here.
So the next talk is scheduled for 17 minutes from now. We can take like a couple of minutes break.
Yeah, sorry, I spoke too fast.
That's not a problem, not a problem. So should be back like in 5 minutes or so. Eu ia falar agora, está passando um carro de som na minha rua, não sei se dá para ouvir aí.
Parecia a televisão ligada, assim.
Não, aqui é comum ter carro de som fazendo propaganda, só que passa muito alto, ele bem na frente aqui.
Que delícia, hein?
Ó. Fazer reunião é complicado. Mas passou já rapidinho. Só que passa cada vez que passa rapidinho, mas passa várias vezes no dia. Clarice, está aí?
Tô, peraí, deixa eu ligar a câmera. Tô aqui.
Boa tarde, como vai?
Oi.
Acho que deve ter provável começar já daqui a um minutinho.
Clarice,
Oi, Ivan, tudo bem?
tudo bem?
Eu vou compartilhar a tela então para ver se tá tudo certo.
Certo.
Ué, peraí. Eu não sei porque que tá com essa margem verde em volta, mas tudo bem.
Eu acho que ele mostra, ele fica em verde a página que você está compartilhando.
Deve ser. Mas se tá todo mundo vendo, tá bom. Eu não sei. Tem algum problema se ficar assim?
Não, nenhum.
Então tá bom.
Eu acho que a gente pode começar já, né?
Fala em inglês ou português? Acho que em inglês, né?
Acho inglês porque pelo evento tá
Tá.
gravando. Embora todo mundo que está assistindo falar português. Só o Francisco mais ou menos que não, mas que em inglês fica tranquilo para todo mundo. Okay, so we can start. Next talk is by Clarice Neto, whose talk is titled Extending Poisson-Nijhuis to Dirac-Nijhuis Structures. Thanks for talking, Clarice. You can start.
Well, thank you for the invitation. It's a pleasure to talk here. And yeah, I will talk about these. Well, my title is a huge title, you know, like we have a lot of structures here that I have to clarify, like what is a Poisson and Dirac and Neuhaus and everything. But we have time to understand these structures. So this is the outline for the talk. First, I will start with some motivations and I have to introduce this structure here, these linear tensors and one derivations to extend the structure that I want to extend, that is the Poisson-Neuhaus. And the second part is Dirac-Neuhaus. Structures, again, is not algebra, it is structures. And the third part is properties. I will briefly talk about some properties of Dirac-Neuhaus structures. So let's start with some motivation. That is the Poisson-Neuhaus structures. So this strange name, this strange structure appears in the context of completely integrable systems maybe in the 18th or earlier 19th in the work of Magdalene Morossi when they study the completely integrable systems with infinite dimension. So this Poisson-Neuhaus thing was important to solve problems in this way, in this direction, because when we they prove it that when we start with a Poisson-Neuhaus structure and we have the integrable systems described by the geometrical structure, they construct algorithm to provide solutions to the integrable systems. In this way, we can construct a second Poisson structure combining the two first, the bivector and this R. Well, I will define in maybe in the next slide what is these things, but in giving a big picture is a smooth manifold, a Poisson bivector, and a Neuhaus tensor. And when we start with, and they have some compatibility conditions, and when we start with these structures, and we have an integrable system described by this structure, they prove it that we can construct a second, not a second, but by recursion, we can construct a lot of new Poisson structures that are defined by Hamiltonian system, and these give rise to algorithm to construct first integrals to systems, to the completely integrable system. So, and we have this property here, that is, this is how they define the first integrals in this system. So by this context, well, the definition of Poisson-Neuhaus thing born with the necessity to construct solutions to by Hamiltonian systems, completely integrable systems. And a second point that motivated us is the holomorphic side of Poisson structures. So when we have a holomorphic Poisson structure, Laurent and Steno and Xu, they prove it that the real part of the holomorphic Poisson structure is a PN structure. So we have this relation here between holomorphic Poisson and Poisson-Neuhaus structures. So this is this structure here, this PN thing, motivated us to extend them, extend these properties here, these 1 and 2 properties, in the more general context. Well, let me draw what we want to found. It's like, in the big way, we will see with more details, we have a Poisson structure, and we can see Poisson structures as Dirac structures. And we have this definition here, that is a Poisson more a Poisson plus a Neuhaus tensor plus compatibility conditions that we will see in the next slide or in a moment. This define a PN structure that have a relation with holomorphic Poisson. And at the same way that we have the relation between Dirac structures and Poisson, that is, when we see the graphic of a Poisson structure, this defines a Dirac structure. We have the same here on this side with a Dirac holomorphic direct structures. So when I say that I want to extend Poisson-Neuhaus thing, what I am saying, what I'm looking for is just for a definition of a direct Neuhaus. There is a direct structure plus a Neuhaus tensor in a certain way that we cover this Poisson-Neuhaus thing. The definition of Poisson-Neuhaus. So, and these direct Neuhaus have some relation with holomorphic direct structure. So we are looking for a definition of direct Neuhaus structure that will cover the definition of Poisson-Neuhaus and is related with holomorphic direct structure. We need to complete this picture here with I draw with the red lines here. So there is the main goal of this talk. So before complete this goal, this main goal, we need to understand little things about Poisson-Neuhaus. There is the object that we want to extend. So let's go. First, I will recall a little what is a Poisson structure. Maybe it's not necessary for this audience, but okay, it's here. So the Poisson structure that I am talking about, I will see using this Schouten bracket and this Poisson bivector. That is a smooth manifold with a Poisson bivector that satisfies this Schouten bracket between pi and pi being 0. And here I have two examples. The first is simple, it's just if m is equal to R3 and pi is given by this structure here. And this is a Poisson bivector. It's easy to see. This is just by the expression for the Schouten bracket Z. Plus, well, maybe here is a minus, but don't matter because this is Z partial with X, and yeah, now this is partial with epsilon and Z X. But well, it's easy to see that this is 0. So here we have a simple example of Poisson bivector in R3. And the second example is more interesting because it's just, well, if we start with this space here, SO3, and taking the cotangent of SO3, and this is our manifold. And here we have this Poisson bivector here. Well, this is a huge expression, and behind this manifold and this pi, this is a Poisson manifold, M with this pi. Well, this is the Hamiltonian formulation of the when we are describing the movement of the rigid body. If we have a rigid body, what we can see as a sphere in R3, and this have the space configuration space given by this SO3, the rotation space. And when we look at the cotangent of this space. This is a Poisson manifold with this bracket here. And the dynamics of rigid body in the R3 is given by the Hamiltonian vector field described by this Poisson structure here. This is I don't know, the Hamiltonian formulation of rigid body in the R3 X space. SO3, sorry. So this is Poisson structure and the samples. And what is a Poisson-Neuhaus structure? Well, a Poisson-Neuhaus, as the name suggests, is just a pair of a Poisson structure and a Neuhaus tensor compatible in some sense. And by compatibility, I am saying that pi and r satisfies these two equations here. And by Neuhaus is just asking for this tensor here being 0, vanishes in, I don't know, in TM. So, what we want to do is extend this Poisson-Neuhaus thing here to Dirac structures. Well, here I wrote in the general way, you know, like in this point, we don't know what is a Poisson-Neuhaus structure, what is the definition, but here we have the exactly definition introduced by Magri and Morosi with these tensors here, this expression here. And well, if we want to extend this definition, you know. So how to do this? Well, we need to look at the compatibility conditions. The first compatibility conditions, there is this compatibility condition here, means that we have this commutative diagram here. And well, we have, if you note, we have the cotangent space, and this vector bundles here over M. And if we look at the second condition, that is this expression here, this has to be 0 to define a Poisson-Neuhaus structure. And if we look at this expression, it's not clear what this means, how to extend this to Dirac context. So, well, we have also alternative description of this tensor here given by Yvette Kosman-Subak, that is using Lie bracket modified by a Poisson bivector structure. But even look at this new way to write this R here, we don't know how to extend this to make sense to Dirac structures. And to do this, we need a new thing that is our second point in the outline of this talk, that is one derivations. And using this one derivation, we will able to rewrite or to extend this Poisson-Neuhaus thing definition. So what is a one derivation? So, and well, it's a known fact that we have a correspondence between derivations on a vector bundle. Here we are in the more general context. We are looking at a vector bundle, arbitrary vector bundle. And it's a new fact that we have this correspondence here between derivations on a vector bundle and linear vector fields on A. And maybe in 5 years ago or more than 5 years ago, Thiago Drummond and Henrique Bursting extended this result to P derivations, not for one derivations and one tensors, but we will focus on one derivations in this thing because we are looking just for Neuhaus tensors. But these generalizations of this result here means that, well, how to define a correspondence between derivations of degree more than 0 and vector fields. There is not vector fields anymore, is tensors on vector bundles. And first, we need the extension of this notion of derivation. And well, we need to know what is a one derivation. There is a triple here, DLR, where D is a map here. There is R linear, L is an endomorphism here, and R is an endomorphism here, and they satisfy this Leibniz typal rule. There is just this equation here. Well, of course, I told that there is a notion of P derivation, and is and maybe in the literature people call this by generalized derivation of degree P, and in this case is a generalized derivation of degree 1, but for simplicity I just call by one derivation. But maybe this definition in the literature called by this huge name. And well, the linear part. What is a linear tensor in this context is just a one-one tensor, J here is called linear if we look at J as a map, we have this vector bundle morphism that is here. J, this descends to Tn, and we have this commutative diagram in this side. So Bursting and Drummond proved that we have this correspondence here, this one-one correspondence here between derivations of degree 1 or one derivations and linear tensors, one-one tensors. Well, this is not magic or anything like this. It's just we have maps between these two things, and we can calculate the expressions of in some cases, and this is that we will see in these examples of this correspondence. Well, the basic example is just the connections. If we start with a connection on a vector bundle, this defines one derivation, and using the correspondence here given by this is a theorem, and using this correspondence here, we can show that we have a linear tensor in the tangent of the vector bundle A that satisfy these equations here. Well, the second example, maybe the most important, not the most, but one of the most important example for this talk is just the holomorphic structure. Well, if we have the holomorphic structure on the vector bundle, well, holomorphic structure here is this triple R, L ends up at a flat connection that they satisfy these things here. Well, we have a flat connection, 1, 0 connection. And when we have a holomorphic structure on a vector bundle, this defines one derivation. Just putting D or map D as a combination of L and the flat connection. This was proved by Henrique Bernstein and Thiago Drummond in this paper called Lie Theory of Multiplicative Tensors. And this example, all these things about that I am saying about one derivations and the linear parts correspondent. This is present in the paper of Henrique and of Bernstein and Drummond called Lie Theory of Multiplicative Tensors. And this example, this holomorphic thing is a section there, if you want to look. And yeah, so we have a holomorphic structure on a vector bundle. We can define a one derivation, and using the correspondence, we have the linear tensor that is just a linear complex structure on the tangent of the vector bundle. Now we have two more examples. There is, for this, we consider this map here, the vector valued map here, and this R is not necessarily linear in principle, but when we do the tangent lift of R, the result is a linear tensor here, and we have a one derivation corresponding. And using the maps that made this correspondence possible, we found the precise expression of this one derivation. If you look, L here is R, and the R is just given by this expression here. So for a tangent lift of a map here, we have the precise expression of the one derivation. You know, like that corresponds to the tangent lift. We have the same to the cotangent lift. Doing a huge calculation is not simple, like is a huge calculation in the paper of Thiago Drummond called Lie Neuhaus bialgebraic. And he proved that these two examples here, that he made this calculation. There is well, and where we do the cotangent lift here, using the correspondence between linear tensor and one derivation, he proved that the one derivation corresponding to the cotangent lift of a map here is given by this triple dr star that is given by this expression here, and L is just R dual, and R is R. Well, you know, like the third member of the triple is just R, the map that we start with. Well, and he proved that we have a relation between them. They are dual. dr and dr star are dual. That means that they satisfy this equation here, dr and dr dual, dr and dr star. Well, so we have our tool, or necessary tool, to revisit the Poisson-Neuhaus case. Summarizing, we have one derivations corresponding to linear tensors, and we will use these to extend Poisson-Neuhaus structure. But before, we have to revisit the compatibility conditions for Poisson-Neuhaus structures. Well, remember that the condition that we don't know how to extend is just this tensor here, that we don't know how to express this in terms of Dirac-Neuhaus principle. I don't know. It's not too easy. It's not easy to see how to do this to Dirac case. So if we look at this expression of R, here we have just dr dual. Look, is that just here? dr star is just this expression here in the definition of R. You know, the definition given by Magdalene Morosi in the 18th. So this expression here appears in this side, and this expression here is just this is L x R. This is the lead derivation of the map R. So we can rewrite this R, this tensor R here by this way. This is just P sharp of dr star and minus dr calculated in pi sharp. Oh, we know pi sharp is too late to say that pi sharp is this map here. It's just look at the bivector as a map, Poisson bivector as this map here. So what we know, what we found is that the compatibility conditions now is just these two equations here. The first equation we don't move, is the same, and the second that is just x for this R, this tensor being 0, is just x for this expression here being 0, and this means this compatibility here. And in terms of diagrams, is just in the first equation, we have this relation here. This is pi sharp, R, and R dual. And in the other side, we have, well, one forms here, vector fields here, one form here, vector fields here, and at this side we have pi sharp, dr, and dr star. So, well, here I put the domain and define the map, these maps correctly. And well, so when we look to the compatibility conditions for Poisson-Neuhaus structures, we just have the compatibility between pi and two one derivations. That is the one derivations corresponding to the tangent and cotangent lift of R. You know, behind this expression of compatibility conditions, we just have the compatibility between pi, dr, r, and dr star, r star, and r. These two one derivations and the Poisson bivector. So this is that are happening in the geometrical side, you know, like if we try to understand this compatibility here, this equation, the huge equation of compatibility in terms of what is happening, what is really happen in the compatibility. What this is saying to us is just that for Poisson structure bivector and a Neuhaus tensor being compatible, we are just asking for, and provide a Poisson-Neuhaus thing, we are just asking for the Poisson bivector and the one derivation, and derivations corresponding to the tangent lift and the cotangent lift of R. They are compatible in this sense here. So this is more easy maybe to extend to direct case. Well, we will see this in the 2 more slides, but before, using this linear side of the correspondence between linear one tensors and one derivations, we can just write the rewrite the compatibility conditions for Pn in the other way, using the linear one tensor side. There is that, and we found that the 2 equations of compatibility here are equivalent to 1 equations in the linear part, you know, in the tangent and cotangent thing. So, well, we have this interpretation of the compatibility equations for Poisson-Neuhaus structure in terms of one derivations here and linear one tensors here. But in our work, we just look at the one derivation side. We don't work too much with a linear one tensor because, well, work in the tangent level of the tangent and the cotangent is not too easy. Sometimes it's a huge calculation. We have to work with a huge number of sections, and we prefer to focus on the side of one derivation. But for, you know, there is a, maybe is more easy to work with this side because we have only one equation. In the case of Dirac is also the same, but we choose to work with the one derivation side. But yeah, at this point, what we have a new way to see the Poisson-Neuhaus structure. That is using one derivation, using this tool introduced by Drummond and Bursting. And well, let's move to direct Neuhaus thing. And before I explain that why this interpretation is good for us to complete that picture that I draw in the beginning of this talk, let me recall that is what is a Dirac structure that I will work with, because, well, Dirac structure is more general than this, because, well, I choose work with the standard Courant algebra. So we can do more general things, but not today. So, well, our environment is the standard Courant algebra. We are here with this structure here, a natural pairing, a projection, and a Courant-Dorfman bracket. And on this standard Courant algebra, we have a definition of Lagrangian subbundle that is, well, L on T plus T star, which satisfies this equation here with respect to the natural pairing. And a Dirac structure here is a Lagrangian subbundle, which is involutive with respect to this Courant-Dorfman bracket. And we call this involutivity by integration property. So, well, this is our Dirac structure. And some examples. Well, I saw that in the beginning of this talk that Poisson structure, we can see Poisson structure as Dirac structure. It's just looking at the graphic. Like if we start with a Poisson structure, the graphic of a Poisson bivector is a Dirac structure. And we have other structure that define the same way, that is the presymplectic structure. If we start with a presymplectic two form here, the graphic of a presymplectic two form is a Dirac structure on or TM, you know, like here. So this is two simple examples of Dirac structures, and let's move to Dirac-Neuhaus thing. What is a Dirac-Neuhaus structure? Well, is a Dirac structure here, also in the standard Courant algebra, and in the using the same spirit of Poisson-Neuhaus thing, is just a Dirac structure plus a Neuhaus tensor that satisfies some compatibility equations in the same way of Poisson-Neuhaus structure. So we define this operator here using this dr and dr star, just in putting in the, remember that we are in the t plus t star. So in the t entries, the tangent entries, we put the dr, and the cotangent entries, we put the dr star. And we have this map here, we put sections of t plus t star and gives sections here. So, well, using this map, we define compatibility between a Lagrangian subbundle of Tm of t plus t star and a Neuhaus tensor here. It's not Neuhaus, well, I'm not calling this L Dirac and R Neuhaus. It's just a Lagrangian subbundle and a map R here, and we say that they are compatible if they satisfy these two equations here. That means L is preserved by R and R dual, because again, these maps is defined here. And the sections of L is preserved by the R, this map, this operator that I defined here. And a Dirac-Neuhaus structure is just a compatible pair, L and R, where L is a Dirac structure and R is a Neuhaus operator. So, what is the one derivation in this language? You know, like I was talking every moment of this talk that the compatibility between Poisson structure and the Neuhaus tensor is encoded by this compatibility between one derivations and Poisson structure, you know, but here in this picture, it's not clear what appears these one derivations. What is the one derivations that I introduced in this talk? Well, it's just here because dr and r star and r is a one derivation on t plus t star. And if you look at this, it's just the sum of these two one derivations that we have before, these dr r in some sense, you know, dr dual, r dual, and r. This defines one derivation, the property of these two one derivations separately implies that this big one here is a one derivations on t plus t star. So in the same way that we have the interpretation of compatibility conditions for Poisson-Neuhaus thing, that is all a Poisson-Neuhaus structure is just the compatibility of a Poisson-Neuhaus, a Poisson bivector with the one derivations that corresponding is corresponding to the tangent lift and the cotangent lift of the Neuhaus tensor. What we have here is just that Dirac-Neuhaus structure is just a pair, a compatible pair. What R, L is a Dirac structure, and this R is this part here of this big one derivation. We have in the we have the same thing. We have a compatibility between a Dirac structure and this one derivation here. So, well, how this recovered our case of Poisson-Neuhaus? Well, before we also have an interpretation of the compatibility condition in terms of the linear part. That is, we have here two equations, the compatibility equations, and using the linear part, the corresponding linear part, we have that the compatibility equations are equivalent to this one compatibility condition in the tangent level. You know, like we are taking the tangent of the Dirac structure and asking for this equation here, this condition here. But again, we choose this one derivation side here to work with and put outside these equations here in the tangent level for a moment. So, well, examples. The first example, the most important one, that is the Poisson-Neuhaus. Well, if we start with a Poisson-Neuhaus structure and look at the graphic of the Poisson bivector, we proved that this pair is a Poisson-Neuhaus structure if and only if this defines a Dirac-Neuhaus structure here. And this is easy to see when we write these expressions, you know, like what is the L pi? This is just these pairs here. This is the pi sharp of alpha, where alpha is element here. So if we ask for example, this condition here, what is the first condition, the Dirac-Neuhaus definition, is just look at this equation here. Alpha. This equation here, and if we expand this, well, this is a Dirac structure, so this have, for this condition being satisfied, we have that we need to prove that this is equal to 0, but this only happens if and only if expanding these things, these let me think a moment. This is letter R. plus R alpha pi beta. This is 0, and this is equal to, well, asking for this is the same of the first equation of the Poisson-Neuhaus thing. That is you know, so in the second equation is the same. We just use the expression of the things to prove that the conditions for being L pi and R being a Dirac-Neuhaus is equivalent to P and R being a Poisson-Neuhaus. It's just a carton calculation, I don't know, it's not too much difficult. And the second example is prosymplectic Neuhaus structure. I don't say before, but there is a notion of prosymplectic Neuhaus thing. There is compatible pair dr omega r, where omega is just a prosymplectic form and satisfies these two equations here. And when these omega r satisfy these two equations here, we call this pair a prosymplectic Neuhaus structure. So when we start with a prosymplectic form and the graphic of this prosymplectic form, we prove it that this is a prosymplectic Neuhaus structure if and only if this defines a Dirac-Neuhaus structure. And the proof is the same, in the same of this Poisson-Neuhaus case here. So we have this correspondence, and this structure here was also introduced by Magri and Morosi in the same context of completely integrable systems, and they use this structure here also to solve some integrable systems, construct algorithm of, I don't know, structures that defines first integrals of certain systems like the KDB, and explicit examples. They define these two structures here to solve some explicit examples of integrable systems. So the third example is just our holomorphic case. Well, when we start with a complex manifold and take this isomorphism here given by this expression, we prove it that this is a holomorphic Dirac structure if and only if L and R is a Dirac-Neuhaus structure. And here we recover the recover our motivation. That is, let me back for a moment. There is, what is it here? We was looking for a Dirac-Neuhaus definition that made this correspondence possible and made this square possible, like extend Poisson-Neuhaus structure. So when we define this in this way that we made here, and looking at the examples that we have, we complete this. We have our goal because we have defined oh, my tablet. Okay. We have defined a Dirac-Neuhaus structure that recover Poisson-Neuhaus structures, in a good way, that means completely recovered. You know, like we have these equivalence here, and I have to make a parenthesis because in other cases there are a lot of definition of direct Neuhaus structure made by other authors, but in these other definitions they don't recover completely. In some cases they don't recover completely these two definitions here, Poisson-Neuhaus and Preliminaries Neuhaus, and we have these equivalents that they don't have in some definitions. And this holomorphic case here is a huge advantage of our definition, because using these one derivations, we proved that we have also a correspondence between holomorphic direct structure and direct Neuhaus structures. And for finish this talk, we have the third part. There is a small part. There is some properties of these direct Neuhaus structures. The first property, maybe this property, well, it's not maybe, but I expect that in the future, in the near future, this property here will be useful to not only extend the definition, because the definition of direct Neuhaus extends the definition of Poisson-Neuhaus and Preliminaries Neuhaus, but also to extend the implication. And by implication, I mean that solve some integrable system, because in the case of Poisson-Neuhaus, they use this hierarchy. Magre and Morosi, they call this property here the property that permit them construct a new Poisson-Neuhaus and Poisson structure, and in this way they describe the dynamics of the system using this Poisson-Neuhaus structure, and to solve the integrable system. And this hierarchy thing play a central role in the solution of integrable system. And we also have a hierarchy of direct Neuhaus structure. Given we have two hierarchies, the first one and the second one, and of course we have some conditions here to recover direct Neuhaus structure, dimensional conditions for maintaining the regularity. And in this way, well, we have hierarchies of direct Neuhaus structure. Maybe we can use this just to construct an algorithm to solve integrable systems described by this direct Neuhaus structure. And you know that in this integrable system theory, non-holonomic systems are described by direct structure. And in non-holonomic systems means that we have systems with constraints, like the ball rolling in the plane, but the ball have to stay and don't give gaps in the plane. And this is the system have a restriction in the velocities. So, and these systems are not described by a Poisson-Neuhaus thing, but is described by a Dirac thing. Maybe if we put a Neuhaus tensor there, we can construct these first integrals, and it's just maybe, but we have a relation between Dirac structure describing non-holonomic systems. We have a relation between Poisson-Neuhaus thing permitting us to solve bihamiltonian systems. Maybe we can use these hierarchies of Dirac Neuhaus to solve some type of certain integrable systems. This is just a maybe, this is just a hope for the future, but this property here seems that we can apply our definitions or definition of Dirac Neuhaus to integrable systems too, like other areas of other fields of mathematical thing. So, well, this is a property that I want to highlight. And the other properties is more geometrical properties, that is the foliation. The foliation of a Dirac Neuhaus structure is a Preliminaries Neuhaus. You know, that Dirac structure have presymplectic foliation. So if we put an extra structure given by the Neuhaus tensor, what happens? What happens is that this Neuhaus tensor in the general thing, in the Dirac level, descends to the leaves, make these leaves presymplectic Neuhaus. And the same thing happens in the quotient. We know it's a fact about Dirac structure that I don't have time to explain, that the quotient of Dirac structure inherits with certain conditions, inherits a Poisson structure. And if we start with a Dirac Neuhaus, what happens with the extra structure given by the Neuhaus tensor? Well, this also descends to the quotient level, making this Poisson structure there, Poisson Neuhaus. So this is a good thing because in the we have these leaves in quotient with a Neuhaus compatible structure in a good way. Well, when we start with a Dirac Neuhaus thing. This what I am trying to say is that the extra structure given by the Neuhaus tensor descends in the natural way to the leaves and to the quotients. And the least thing that I want to mention about Dirac Neuhaus structure is just that we have integration. Integration in the sense of looking at the Dirac Neuhaus structure as a Lie algebroid, and we have that this Dirac Neuhaus structure is a small part, is an infinitesimal part of a presymplectic Neuhaus groupoid. Of course, with some conditions, we have to explain more about it, but in avoiding the conditions, we have this integration here that is the Dirac Neuhaus structure, looking at same as a Lie algebroid, is just the infinitesimal part of a presymplectic Neuhaus groupoid. And as we have the correspondence between Dirac Neuhaus with holomorphic structure, we also have as a corollary of this integration result, integration of holomorphic Dirac structure to groupoids, to holomorphic presymplectic groupoids. So it's all. Thank you for your attention.
Thank you, Clarice. Does anyone have any comments or questions?
Hi, Clarice.
Hi.
No, I was waiting to ask you about the integration. So this is good that you talked about integration. So I wanted to ask something else. So somehow is there, I don't know if there are applications of this, but so if I understand correctly, you have this foliation, which is Poisson Neuhaus or presymplectic Neuhaus. So you have you can think about these hierarchies like a foliated hierarchy or something, or
yeah, in the one direction we have when we have this when we look at the one of them, these two hierarchies, we have also in the leaves hierarchies of presymplectic Neuhaus. This because I told more about Poisson Neuhaus theory, but the hierarchy history here is also constructed by Magri and Morosi for presymplectic Neuhaus too. So they defined hierarchies for presymplectic Neuhaus in the same way, but in the recursion relation with the omega and R. And when in the Dirac Neuhaus case, in the leaves, we have in the in one direction, maybe in the second direction. No.
So,
Maybe
and in the transverse direction, do you know what happens? So do you have like a splitting theorem or something like that?
I don't have it, but it's not. It's a thing that someone asked for Enrique and Thiago and me, but we don't have simple answer because it's not too simple to split something. We lose some information in the vertical side, you know, and we don't know, for instance, how to characterize the things that we lose when we do this process. But it's a good question. We have to think about it.
Thank you.
Thank you.
So I guess there are not more questions or comments. Thank you again, Clarice, for participating in our session.
Thank you.
It's a very interesting talk.
Thank you. I stopped my presentation for.
Oh. Okay, so next we have Gonzalo Andrés Moya Navarrete. Hola, Gonzalo.
Buenas tardes.
Para ti.
¿Se me escucha?
Sí, sí.
You listen me?
Yes.
All right.
Could you give your talk in English or if you're not comfortable
Mi
with
presentación va a ser en español.
Ah, está bien, está bien.
Perfecto. Bueno.
Bueno.
Me presento, soy Gonzalo Moya Navarrete. Voy a bajar un poco el volumen porque rebote. Gonzalo Moya Navarrete, pertenezco al Departamento de Matemáticas y Física de la Universidad Católica de Temuco. Y mi tema que voy a exponer corresponde a la simulación de parámetros geométricos superficiales y volumétricos para un ala bidireccional de una turbina de media potencia tipo Michel-Vanki. Deme un minuto, por favor. A ver.
Bruno, ¿sabes si se está grabando esta parte?
Excuse me. Give me a little second, but start the presentation, please.
Okay. ¿Qué pasó, Francisco?
Preguntaba si tú sabes si esta parte se está grabando.
Sí, está grabando.
Ah, ok.
That's right. Ok. Perfecto.
Ahí lo vemos bien.
Ok. Nuevamente. Mi tema es la simulación de parámetros geométricos superficiales y volumétricos para un ala bidireccional de una turbina de media potencia tipo Michel-Vanki. Mi nombre nuevamente es Gonzalo Moya Navarrete y pertenezco al Departamento de Ciencias Matemáticas y Físicas de la Facultad de Ingeniería de la Universidad Católica de Temuco. Como introducción, la conformidad de la simulación de parámetros geométricos superficiales y volumétricos del perfil de una ala bidireccional de una turbina de media potencia, siendo esta de tipo Michel-Vanki. A nivel de aplicaciones, a nivel superficial, existen parámetros geométricos euclidios que se pueden aplicar a métodos de que tienen relación con procesos industriales correspondientes a los sistemas de control numérico CNC, y mediante trayectorias de funciones de trayectoria o ecuaciones de trayectoria, y a partir de esto, de velocidad, se puede determinar aquello, sabiendo que el material del ala bidireccional es un material isentrópico que corresponde a un hierro fundido. Y así muchas otras aplicaciones. Y la parte volumétrica puede servir para un análisis hidrodinámico, conociendo la geometría euclídea de este elemento en R3, y luego conociendo la geometría y los elementos de volumen de aquello a nivel analítico, se puede determinar desarrollar el análisis hidrodinámico de este. Antecedentes energéticos en Chile. A diciembre de 2019, la matriz energética nacional tenía 6.679 megawatts de capacidad de potencia instalada hidráulica, correspondiente al 28% de la matriz energética en Chile. Sobre la capacidad instalada hidráulica disponible principalmente para uso industrial y doméstico, esto corresponde a la potencia neta. Cabe recordar que está la potencia instalada, que es lo que sale de la central a través de la red eléctrica que abastecen de energía a una localidad, y lo que es potencia neta, lo que nosotros ocupamos. Existen dentro de esta las grandes centrales, que en Chile se conocen la más importante como la Ralco, con 690 megawatts, Pangue, 456 megawatts, El Toro, 450 megawatts, y Rapel, 350 megawatts. Estos datos mencionados están de acuerdo con lo que rige según la solicitud de centro de despacho de carga, de organismo perteneciente al Ministerio del Interior del Gobierno de Chile. A continuación voy a poner algo más específico con respecto a lo que se está desarrollando con la generación de mediana potencia. En Chile, la más conocida son las centrales de media potencia. Está Florida 2 con 20 megawatts, Chiburgo con 19,1 megawatts, Los Molles 18 megawatts, Providencia con 14,2 megawatts, Guayacán con 12 megawatts, y finalmente Chapiquiña con 10,8 megawatts. Generalidades sobre el diseño de la turbina o turbomáquina generadora de media potencia tipo Michel-Banky. El ala bidireccional de la turbina es, como decirlo, el segundo componente de mayor importancia que tiene la turbomáquina. Cabe señalarse que el de mayor importancia es el rotor, porque es el elemento que transforma la energía hidráulica proveniente de la compuerta de cualquier turbina, y el segundo en este caso es la ala bidireccional. ¿Y cuál es la importancia real de esta? Que encausa el flujo de dirección que proviene de la compuerta y llega hasta el rotor. Entonces, ¿qué es lo que sucede ahí? A veces por golpe hidráulico, hay mayores velocidades que hacen que se rompa la capa, haya turbulencia y se rompa el concepto de capa límite dentro del flujo. ¿Y qué es lo que hace aquello? Encauzar el flujo de manera ordenada para que no suceda esto. Ahí tenemos un esquema transversal de cómo circula el flujo, el caudal en este caso, de manera la mitad hacia arriba y la mitad hacia abajo, dentro, como si mirándolo de perfil, el ala bidireccional. La formación con la construcción de la potencia de la turbina de media potencia generadora, existe un conjunto de análisis que se centran en planos de fabricación, y esto fue desarrollado en el país de Nepal entre los años 1975 a 1980 por la Woodball Engineering Works, y que fue publicada por la Deutsche Zentrum für Entwicklungstechnologie, que es el Centro Alemán de Tecnología para el Desarrollo. En paralelo, se trabajó, en paralelo con la Woodball Engineering Work, trabajó la German Exchange Technology Appropriator. A esto se tiene que considerar de esta información los planos de fabricación que están en la figura 2, 3, 4 y 5. En la figura 2 corresponde a una vista general de la turbina de media potencia, que lo que está mostrando es ¿cómo decirlo? Es una vista general, un layout. Y en rojo se muestra dónde se encuentra el ala bidireccional dentro de la compuerta, que es un elemento robusto, porque tiene que soportar presiones altísimas de flujo. Ahí tenemos una vista panorámica del ala bidireccional. Y el perfil de como lo indica, se puede modelar claramente dicho contorno. El perfil está al lado izquierdo y la vista de elevación está a la mano derecha. Ahí hay un plano de fabricación del perfil del ala bidireccional, donde yo me basé para hacer el análisis geométrico superficial para determinar ecuaciones de contorno, que lo voy a ver más adelante. Y finalmente ahí hay un modelo tridimensional, cómo se vería, cómo es el elemento en sí. Contorno del perfil superficial para el alave, o en el alave. Sobre la descripción de algunos aspectos geométricos experimentales determinados mediante ecuaciones analíticas, el perfil del ala direccional a la turbina de media potencia tipo Mitchell-Banke se realizó mediante un conjunto de ensayos durante un tiempo determinado. En el año 2014, cuando yo realizaba mi memoria de título en ingeniería mecánica, y que ahí empezó el trabajo en sí, donde sin mayores herramientas, logré determinar mediante mediciones un modelo analítico aproximado del contorno del perfil del ala bidireccional. Como aspectos geométricos, la determinación de las ecuaciones de contorno del ala bidireccional, como cabe mencionar, es un ensayo de mediciones, y estas son longitudes equivalentes que fueron medidas punto a punto en sistemas coordenados cartesianos experimentales. Y esto también utilicé elementos de geometría descriptiva para poder encontrar dichas ecuaciones, que en primera instancia, por ejemplo, había una ecuación logarítmica en plano cartesiano y una ecuación polar de una espiral que conforma el contorno, un trazo de la superficie del perfil. Bajo estos conceptos, en primera instancia, sobre mediciones experimentales, yo había determinado 7 dominios cartesianos para 7 ecuaciones distintas, lo que al final quedaron en 3. Y en esta quedaron una estándar X, una referencial U y B, y otra referencial alfa beta. En la U y B, U, B, la referencia cartesiana U, B, yo había determinado que estaba en rotación con respecto a la estándar X, cuyo ángulo, y le adelanto, cuyo ángulo de rotación es menos 65 grados, y le adelanto sobre la referencia cartesiana alfa beta, que se encontraba en traslación con respecto al estándar X de 89,-54, esto está medido en milímetros, pero por comodidad del análisis yo lo omito para que quede claro, y los ángulos que están referenciados están en radianes. Ya como venía diciendo, para alfa beta, ¿cierto? Está a 89,-54 milímetros, y el ángulo de rotación que existe es de 150 grados, lo cual para la referencia U, B equivale a 59,36 por pi, y para el alfa beta, con respecto a la traslación dada, corresponde a 5/6 de pi. Sobre los dominios coordenados cartesianos, la nomenclatura correspondiente, y que también se va a ver más adelante para dar a conocer la ecuación de contorno, el dominio coordenado estándar, el XY, corresponde a los trazos C y D y OD, los trazos geométricos. El dominio de rotación con respecto al sistema coordenado estándar, que es el U y B, y para el correspondiente al arco OB, y el dominio de rotación y traslación en función del sistema coordenado estándar, U y B, denominado dominio coordenado alfa beta, correspondiente al al arco B y C. Aquí doy a conocer los distintos vértices de que están compuestos los trazos geométricos del contorno de la superficie de la lava. Permiso. Aquí, para referenciar la traslación del sistema coordenado estándar, XY, doy a conocer un sistema coordenado en traslación a este, y lo denomino X' y', donde ahí se referencia el ángulo de rotación con respecto al estándar, que es como se muestra, son 5/6 de pi. El dominio coordenado cartesiano se estableció como sistema estándar para el trazo geométrico rectos que componen el perfil de la lava, donde el trazo geométrico OB, que corresponde al dominio cartesiano U y B, y comparten el mismo origen. Y como se indica, es 65 grados sexagesimal en sentido horario. Dentro de la construcción geométrica, y que con esto quisiera también adelantar un poco, que la ecuación característica del arco geométrico OB corresponde a la ecuación en el dominio U y B, como lo indica la ecuación número 1, que es B es igual al logaritmo natural de U más 1. Pero ojo, dentro de esto existe un factor de escala, que en este caso el factor de escala, sistema coordenado cartesiano, experimentalmente, justamente está el factor de escala. Este factor de escala, para el trazo, para determinar experimentalmente la ecuación analítica, se tiene que haber hecho un un símil entre modelo prototipo, y este símil entre modelo y prototipo correspondió a una relación de 1:20, lo cual lo puedo describir mediante una fracción de 1/20. Lo cual, entonces, llego a proponer, mediante esto, que el análisis experimental lo doy más adelante, propongo la ecuación número 3, B en función de U, igual a 20 logaritmos de U más 20/20 para todo U en 0,106 milímetros, presupuestamente, pero como ya había mencionado anteriormente, omito la nomenclatura con respecto a las unidades de medición. Permiso nuevamente. Los valores experimentales que fueron medidos mediante para el dominio cartesiano fueron, si lo podemos representar de manera cartesiana, abscisa ordenada, están dados por la tabla 1, ahí se ven 10, 30, 50, 70, 90, 106, y que hubo un mínimo error con respecto a la expresión analítica. O sea, un error casi un 0,000, o sea, casi nada. Y aquí doy a conocer la forma geométrica de la ecuación analítica que planteo con respecto a la ecuación que me baso para poder hacer para poder desarrollar la ecuación característica del contorno para este trazo. Disculpen. Ahora sí. Bueno, está el esquema geométrico que muestro aquí, correspondiente, y justamente si uno lo ve, hace una comparación, es casi idéntico, mejor dicho, es idéntico a la ecuación de característica para este trazo. Ahora hablaré en el dominio coordenado alfabeta que corresponde al contorno B y C, al arco geométrico B y C, cuya ecuación característica en plano polar correspondería al radio polar, equivalente a 20 veces la exponencial del ángulo azimutal sobre 5, o sea, R igual a 20 por E elevado a θ quintos. El dominio coordenado cartesiano, alfa beta, que se muestra en las figuras 9 y 10, correspondería a la experimentación del contorno del arco geométrico B y C, donde el factor de escala es el mismo, pero de manera inversa. O sea, si yo en el modelo prototipo anterior había propuesto 1/20, ahora es 20/1, lo cual esto me da sobre lo que yo planteo que sobre lo que yo planteo que tengo un perfil que fue ensayado experimentalmente, y a través de esa experimentación yo pude determinar una pseudo característica que al final me da una ecuación característica de por sí, que también tiene un cierto grado de error, pero este también es mínimo. Y está expresado mediante una presión en un plano polar. Aquí en esta representación cartesiana está referenciado para eje alfa y beta, o beta, perdón, alfa f de alfa. Y aquí quisiera ver que, no sé, podemos imaginar que esta espiral logarítmica que tenemos para de 0 a 2pi tiene mucha similitud con lo real, con lo experimental. Mediante, como ya había mencionado, mediante el par X, Y, que representa el dominio cartesiano en traslación con respecto al dominio cartesiano estándar. ¿Me disculpan, por favor? Gracias. Con respecto al estándar, existe una mayor complejidad en el análisis por sí, ya que si podemos referenciarlo con respecto al dominio estándar XY, se genera mayor tediosidad en el análisis algebraico para determinar, ya sea, no sé, por ejemplo, el área, elementos de área, varios conceptos geométricos implicados con el cálculo infinitesimal. La ecuación cuya forma polar en el plano propolar, valga la redundancia, corresponde al dominio coordenado cartesiano alfa beta, que en un primer momento, dicho contorno de la superficie del perfil del ala B, se determinará una forma experimental mediante técnicas también de geometría descriptiva, de manera que la tabla 2 a continuación mostraremos el rango del dominio, los valores en el rango del dominio alfa beta para el caso arco geométrico BC, cuya distancia con respecto al origen coordenado, punto contorno, corresponde a la expresión R sub E, que es el radio polar experimental. Y ahí yo doy a conocer lo experimental, y va muy similar a lo que yo digo con lo analítico. Es muy similar. O sea, uno dice, por ejemplo, para 120 grados, no doy a conocer toda la cantidad de decimales. O sea, lo acoté en 2 decimales. Más que nada de manera explicativa. Igualmente, o sea, como si para U igual a, perdón, para B igual a U más 1, logaritmo de U más 1, R es igual a E a la teta, al aplicar el factor de escala quedaría como ya había mencionado anteriormente, y que lo vemos en la ecuación número 6, R igual a 20 E a la teta quintos. Fue punto a punto mediante un calibre. De primera fue un calibre manual, después fue un calibre electrónico, y que utilicé utilizando, volviendo al anterior, el plano de construcción de la figura 5, si no me equivoco, que dije anteriormente. Lo cual yo hice de la última medición 9 puntos distintos para el radio polar experimental, que está escrito en la tabla número 2 anterior. Y ahí doy a conocer la forma de la distancia experimental mediante el radio experimental descrito. expresión en radianes y la expresión analítica que evaluada en dicho ángulo polar. Como vemos, por ejemplo, para 120 grados habíamos dicho 30.41, tenemos aquí un radio equivalente analítico como 30.40512. O sea, 30.41 si lo aproximamos. Ahora hablaré sobre la construcción experimental del contorno. El dominio coordenado estándar, vuelvo a mencionar, de manera medible, referenciándolo según la disposición geométrica de la superficie del perfil para la bidireccional. Se debe tener presente que la información que soluciona el problema a nivel tridimensional es el centro de inercia, o el momento de inercia es total para volumétrico, en este caso del elemento del ala, visto como un sólido rígido. La representación geométrica del perfil para el punto coordenado A, que vemos aquí, corresponde al centro de máxima eficiencia según la literatura en que yo me basé, pues de los ensayos de ingeniería hechos en Nepal por la German Exchange Applicator Technology, no me acuerdo bien, pero bueno, que eso fue en conjunto con la Deutsche Zentrum für Technologien, y lo llevó a cabo la empresa alemana Woodball Engineering Work. Y este punto de máxima eficiencia, si uno, por la simetría que existe, porque estas son placas planas que tienen esta curvatura geométrica, pero en otras palabras son, como ya había mostrado el elemento tridimensional, son dos cilindros macizos unidos por una placa transversal que está inclinada. Entonces, supuestamente, se supone que según esto, se correspondería, y eso es motivo de estudio actual, que correspondería al centro de inercia, al momento de inercia a nivel tridimensional del sólido rígido. Las ecuaciones correspondientes al dominio estándar, x, y es x, como son trazos rectos, x igual a 0 para y de 0 a 4 y y igual a 4 para x de 0 a 78 milímetros. Con respecto a la figura 11, el origen del dominio coordenado cartesiano estándar por simplicidad coincide con el origen del dominio coordenado U, lo cual en función de este va rota el ángulo que corresponde, vuelvo a mencionar, menos 65 grados, que en otras palabras es 59 partido por 36 multiplicado por pi. Y en esta tabla yo doy a conocer la rotación de ejes coordenados para finalizar esta sección. Los ángulos de la rotación en sentido sexagesimal en el sistema radial, la nomenclatura de que para el ángulo que rota el dominio U, B, lo denominé como mu, y para el que rota alfabeta con respecto al estándar, lo denominé como lambda. Obviamente, si comparte el mismo origen cartesiano, va a ser 0, 0 el par de traslación, pero el OE, el trazo OE del vector de traslación correspondería, según lo que yo planteo, 89 menos 54. Construcción. Ahora doy a conocer la construcción geométrica de la superficie del perfil del ala direccional. La construcción geométrica de la superficie del perfil direccional correspondería al volumen total, o sea, correspondería como fin último el de la determinación del volumen total del perfil del ala, que como ya planteo a través del punto A de las figuras anteriores. Permiso, por favor. Gracias. Como planteo anteriormente, el punto A del perfil del ala B direccional es la reflexión, perdón, no, es la proyección de la línea de acción del centro del momento de inercia del elemento mecánico que es el ala direccional del perfil. Como objetivos está la ecuación de contorno superficial del ala direccional, análisis de continuidad, que no lo daré a conocer en este minuto por temas de tiempo, y la determinación del conjunto de valores posibles para el vértice C. Y eso me parece muy interesante, algo que se les puede compartir más adelante. La ecuación de contorno del perfil del árabe ya la habíamos dado a conocer anteriormente, pero en esta figura yo doy mediante un graficador, haciendo el análisis de traslación y traslación para otro. Claro, aquí está editado, pero en sí está editado el tema de las ecuaciones para dar a conocer cuáles son las ecuaciones del contorno para los trazos geométricos. Están en función del dominio de coordenado estándar. Disculpen. Ahora sí. ¿Se me escucha? ¿Aló?
Fuerte y claro, Gonzalo.
Sí, se escucha. Sí, se
Sí, se me escucha. Perfecto. Gracias. Entonces ahí, como doy a conocer la gráfica mediante las ecuaciones de contorno para los trazos geométricos. Perfecto. De acuerdo a esto, la ecuación de contorno superficial de la direccional corresponde a la geometría de la superficie, como se ve claramente visualmente. Está la geometría contornos rectos y los contornos curvos. Vuelvo a mencionar que el dominio coordenado referencial, por su naturaleza, contiene ecuaciones de contornos rectos, y el dominio, y los otros dominios, que el U y B y alfa beta, corresponden a los dominios de los trazos curvos, que son el trazo OB y el trazo BC. El dominio ordenado rectangular, ahí ya vamos entrando en materia más específica, como está planteado para todo XY de R0 más a cruz R, está dado la ecuación de contorno rectas. Para el dominio coordenado U y B, está dado la ecuación es que la ecuación de contorno para el arco geométrico OB, con la expresión número 9, descrito más algebraicamente. Bueno, si hacemos la traslación y rotación, perdón, solamente la rotación, ¿cierto? Y planteemos la ecuación y su dominio, donde está descrito el dominio coordenado estándar, que ahí se ve en la ecuación número 10. Y ahora, yo quisiera, porque también falta un poco para determinar con taxatividad la determinación del conjunto de valores posibles para el vértice C, y que también puede ser, se infiere que también puede determinarse para cualquier punto del dominio coordenado cartesiano alfa beta. Existe un punto de convergencia entre el dominio coordenado cartesiano XY y alfa beta, descrito mediante un vértice del par en el dominio coordenado estándar, que equivale a 78,4. Las ecuaciones que convergen en dicho vértice son expresadas por las variables referenciales características, y estas corresponden, aquí hay un esquema sobre las ecuaciones, ya sea por su forma polar y su forma cartesiana. El trazo recto CD, ¿cierto?, es la ecuación equivalente a I igual a 4. Y la ecuación característica del arco BC es, en su forma cartesiana, la raíz cuadrada, ¿cierto?, de alfa cuadrado más beta cuadrado, equivalente a 20 por E elevado a un quinto de tangente alfa sobre, perdón, beta sobre alfa, que está en correspondencia a su forma polar. ¿Cierto? Aplicando el modelo de rotación y traslación, ¿cierto?, de forma matricial, como se muestra en la ecuación número 12, al desacoplar, al describir las variables X y Y del dominio coordenado estándar en función de alfa beta, desacoplando cada una de las ecuaciones involucradas, formulamos la ecuación número 13, que se ve aquí en la diapositiva. Según la ecuación 13, en la segunda ecuación desacoplada en función de alfa beta, y igualando a la ecuación 4, o sea, I igual a 4, reemplazamos y determinamos la ecuación 14 en función de alfa beta, lo cual esta ecuación 14, al aplicar la transformación a un dominio polar, siendo para alfa R coseno de teta y R seno de teta, ¿cierto? Que esa es la transformación natural de un dominio coordenado a un dominio polar. Lo cual llegamos a proponer que este tramo recto CD va a corresponder a la ecuación 16. Y la ecuación polar del trazo de contorno superficial del arco BC está dado por R20E a la teta quintos. Entonces, igualando ambas ecuaciones, R igual a R, proponemos a la última ecuación que se ve en la diapositiva, ¿cierto? Que 29 décimos igual equivalente a E elevado a teta quintos, todo multiplicado por el factor de coseno de teta menos raíz cuadrada de 3 multiplicado por seno de teta. Mediante esta igualdad que vimos anteriormente, yo puedo formular una función, ¿cierto? Sabemos que estamos en un plano, en R2, entonces yo tomo ambas igualdades y las igualo a un tercer término trivial, o sea, 0, lo cual me queda, este 0 es igual a f de teta, que podemos decir que f de teta puede estar dado para un intervalo 0 a 2pi, pero vamos a ver adelante, que hay una cosa media extraña ahí, porque aquí en la gráfica, si vamos de 0 a 2pi, ¿está cierto? Vamos a un siglo, no hay, no lo hay. Si de 0 a 2pi, no lo hay, no hay un valor equivalente dado que pueda satisfacer la igualdad dada. Perdón, me equivoqué. Sí lo hay, pero para eso vamos a ir más adelante. No sé por qué me desconcentré un poco, perdón. Sí, claro que lo hay, sí, porque 2pi sería 6,28 y ta. Eso. Así que, formulando un método numérico, que vamos a decir que f de teta menos f de teta más 2pi debe ser distinto de 0. En el vértice C, correspondiente al dominio coordenado cartesiano alfa beta, se deja en evidencia el cuadrante que se encuentra en el cuadrante 4. El ángulo polar θ debe cumplir la condición que éste pertenezca a 3 medios de pi hasta 2pi abierto, es un intervalo semiabierto, pero con una condición adicional, que existe un n para cada revolución, que n pertenece a los enteros. Y ahí eso lo veo aquí en la representación geométrica del perfil del ala B, que está para el valor de θ descrito anteriormente. Según la gráfica 13, se considera como la condición del valor inicial, el par 0,-12 quintos, que satisface, ¿cierto? Satisfacería un valor para θ igual a 0. Pero además es necesario decir que en dicha función debe ser f de θ igual a 0, tal que f no pertenece a 2pi, perdón, al intervalo cerrado 0, 2pi. Según esto, podemos decir que e elevado a θ quinto por seno de θ más pi sexto es distinto de 29 décimos, para no existiendo f de θ igual a 0 para todo θ de 3 pi medios, 2pi cerrado. Entonces, yo creo que todos le vienen en este minuto el interrogante. ¿Por qué yo digo que, y me disculpen, voy a volver atrás para hacer hacer la explicación? Claro, tenemos que en el cuarto cuadrante existe un valor no crítico, pero además existe, en la gráfica existe un valor crítico, pero a eso, perdón. En otras palabras, me voy no a la parte derecha, porque en la parte derecha existen los valores críticos de por sí, ¿cierto? En 2pi creo que está en valor. Me voy a la parte izquierda del semiplano derecho. Y en la parte izquierda del semiplano derecho, teta, f de teta, yo veo estoy tratando de buscar los valores críticos para el intervalo del cuarto cuadrante. Si elegimos un valor de n en los naturales, tal que existe un teta 2 en un intervalo cerrado de 3pi medios a 2pi más 2pi n, la función f de teta adquiere el valor e elevado a teta quinto por seno de teta más pi sexto menos 29 décimos. Pero si le damos a esta función una revolución en el plano, o sea, le adicionamos un 2pi, vamos a obtener la ecuación característica a la ecuación 20. Lo cual, esta ecuación 20, en función a la ecuación 19, que es f de teta igual a e a la teta quinto seno de teta más pi sexto menos 29 décimos, la podemos expresar como f de teta más 2pi es equivalente a decir a e elevado a 2/3 de pi menos 1 multiplicado por el factor f de teta más 29 décimos más f de teta. Las funciones f de teta y f de teta más 2pi mantienen invariantes bajo la transformación del ángulo azimutal teta. Además, se hace necesario determinar el valor del ángulo azimutal teta para un parámetro de que denominaremos como gamma, cuyo valor correspondiente de esta parametrización se establece que es 0,1 cerrado dicho intervalo. Si solo así teta se encuentra en el cuarto cuadrante, pero este cuarto cuadrante va a ser un intervalo cerrado. Dicha parametrización para el ángulo teta va a corresponder que teta sub gamma va a ser equivalente a 3 medios de pi por gamma más 2pi multiplicado por el factor de 1 menos gamma. El carácter de la parametrización de teta sub gamma es decreciente, y de otro modo lo podemos expresarlo como 3 medios de pi multiplicado por 1 menos gamma más 2pi gamma para todo gamma, o sea, para todo teta sub gamma, equivalente al intervalo cerrado 3 medios de pi, 2pi. Entonces tendríamos que la diferencia entre las funciones f de teta más 2pi menos f de teta sub gamma, que para teta gamma, que es la parametrización de teta, es equivalente a la ecuación 24 en su miembro derecho. Esto hace necesario un elemento equivalente para la igualdad correspondiente de esta diferencia expresada por la ecuación 24. En efecto, existe que se cumple la igualdad siendo que el elemento parametrizado va a ser equivalente a pi sexto. O sea, teta sub gamma es igual a pi sexto. De esta manera, cumpliendo la igualdad, diremos que la diferencia de la función f de teta menos 2pi, perdón, a ver, más 2pi, me equivoqué en la redacción, más 2pi, perdón, menos f de menos pi sexto, ¿cierto? Y que lo que estamos expresado en la ecuación es 26, va a ser igual a 0, porque, a ver, tenemos el término multiplicado por seno de pi sexto menos pi sexto, esto es seno de 0, 0, y todo un número multiplicado por 0 es 0, por lo tanto esto es 0. Considerando que al determinar el valor angular del parámetro teta sub gamma igual a pi sexto generado, podremos decir que f de teta gamma más 2pi menos f de teta gamma es equivalente a 0. Por lo tanto, si existe en esta diferencia de las dos funciones que además están parametrizadas por gamma, la diferencia es 0, entonces por lo tanto estos dos elementos son iguales, pero tiene que cumplir la condición que el parámetro sea igual a pi sexto. Por lo tanto, existen dos valores, 11 pi sexto y menos pi sexto, asumiendo una nueva variable, la cual denominaremos teta gorro, me faltó, pero este teta gorro también cumple la condición de que está en el mismo intervalo cuyo dominio es un intervalo cerrado. Entonces, vamos a asumir que este f de teta gorro es e elevado a teta gorro quinto seno de teta gorro más pi sexto menos 29 décimos igual a 0. Por lo tanto, f de teta gorro más una revolución que es más 2pi es f de teta gorro más e elevado a teta gorro partido por 5 multiplicado por seno de teta gorro más pi sexto factor de 2 quintos de pi menos 1. Por hipótesis, asumiremos que f de teta gorro es igual a 0 y e elevado a teta gorro quintos seno de teta gorro más pi sexto es igual a 29 décimos. En consecuencia, podemos expresar que la suma de teta gorro más 2pi es cuya resultante debe ser distinta de 0, tal que teta gorro está dentro de ese intervalo cerrado que se está mostrando a continuación en la parte superior. Por lo tanto, este teta gorro no tendría punto crítico. La gráfica en el plano polar rectangular f de teta, teta f de teta está generado por la curva de la espiral logarítmica, como se muestra para dos revoluciones, y así perdone. Si lo centramos en el cuarto cuadrante, ¿cierto? Vamos a encontrar un valor para cada una de las revoluciones, ya sea la ecuación cuando n vale 0, cuando vale 1, cuando vale 2, y así sucesivamente. Ahí está solamente restringida la ecuación para n igual a 0 y n igual a 1, que supuestamente van a dar valores cíclicos. Si el ángulo teta gorro se encuentra, como lo especifica la gráfica, en el ala direccional, el perfil del ala direccional para el dominio alfa beta, en el sistema, claro, como lo especifica el cuarto cuadrante, por definición del dominio de teta gorro existe un punto equivalente a 0. Una hipótesis de esto es la figura 15 en rotación para el ángulo simutal teta. La segunda rotación de este existe un punto en el dominio de este ángulo equivalente a 0. El elemento descrito como par perteneciente al cumplir el cuadrante debe ser equivalente a este, ya que se cumple la igualdad de teta gamma, el teta parametrizado bajo para la función, o sea, la función de teta sub gamma más pi sexto es equivalente a f de teta sub gamma. Y además con este desfase, yo puedo formular que encontrar un valor para teta dado que me pueda dar un valor polar para el radio polar donde está el vértice C del perfil del ala direccional. Y después de haber sacado las cuentas, yo concluyo finalmente que este valor de C es pi sexto. Las cuentas no están descritas, esto está, lo anterior está descrito a grosso modo. Esto también se justifica mediante el teorema de máximo y mínimo. Sin detención en dicho teorema se determina el valor crítico del ángulo θ sub c, por ende. Ahí están sacadas las cuentas en la parte superior derecha, en la parte superior de la diapositiva, donde existen, para determinar el valor crítico de θ sub c, dos condicionantes, ¿cierto? Por el álgebra elemental se lo puede sacar, calcular la presión 33. ¿Ya? ¿Cierto? Sabemos que no es correcto la condicionante de izquierda, no es correcto, por lo tanto no pertenece a lo real y necesitamos un valor real. No lo podemos ir a un plano complejo si estamos en una situación real, o sea, una superficie real, algo que se ve. Entonces no podemos irnos a un conjunto mayor que el conjunto de los complejos. Y por lo tanto, esto no pertenece a, es distinto, debe ser distinto de cero. O sea, sabemos de antemano que cuando tenemos una función exponencial, el recorrido de toda función exponencial va de cero abierto, o sea, no es el cero hasta infinito. Por lo tanto, le quedamos con la condicionante derecha. Para todo c mayor o igual que cero. Y según este bisexto, podemos encontrar el valor final y que está escrito como θc. Con dos condicionantes. Esta condicionante está dada para el valor de θc, que está dada por con el valor final entre la llavecita, claro, entre la llavecita derecha. θc es igual a la cotangente a la menos 1 de menos 1/5 menos pi sexto, y el θc es la tangente, o la tangente a la menos 1 de menos 5 menos pi sexto. Lo que debemos tener presente siempre para esta condicionante, la gráfica de la tangente en un plano xy, h de x, tangente de x, que lo representamos acá. Y a través de esto, o sea, yo me quedo finalmente. Esto quizás puede demostrar que porque ya con esto, con el θc, ya encuentro el valor de θc para un R de θc, que no especifiqué, o sea, no es que no haya especificado, pero ahí llegó ya a un resultado, ya llegó al resultado dado. Y esto podría demostrarlo, ¿no? Aún en materia de estudio. Y si demuestra eso, puede ser para cumplirse para cada uno de los radios del contorno del dominio coordenado alfa beta. Y esto sería mi presentación en memoria de un ex compañero José Luis Cruz Paco. Y en la bibliografía está de esto referenciada a Breslin, que es una literatura muy específica de ingeniería. Está la German Appropriate Technology Exchange, que se me había olvidado en su momento, Deutsche Center für Technology in Small Water Turbine, Instruction Manual for the Construction of Cross-Flow Turbine, escrito por Helmut Schauer, Reinhold Metzer y Bob Jodach. Y después hay otros autores, pero esta bibliografía es histórica, exceptuando mi memoria de título que está referenciada aquí, con que yo obtuve el grado de ingeniero mecánico. Que está la referencia histórica hasta Costa Pereira y Borges, que en la University of Lisbon está, bueno, también hay literatura asociada como George Afken and Hans Weber, Mathematical Method for Physicists. Está Steinen, Schiffau, Arthur Stuck, Mathematical Method for Physicists. También está Gonzalo Moya, que es el que les habla, que fue su memoria de título para tener el grado de ingeniero mecánico. Y está este autor que, bueno, yo no tengo idea de coreano, me van a perdonar. No sé, algo así, que es... y el último, Ian Struve, Theory and Design of CNC System, de la Springer Verlag, London Limited, London, United Kingdom, el año 2018. Eso sería mi presentación, por favor. Gracias.
Rafael, muchas gracias por tu presentación. ¿Alguien tiene alguna pregunta o comentario?
Por favor, preguntas o no quedó claro. Por favor.
Si no hay preguntas, agradezco nuevamente tu participación, Gonzalo. Muchas gracias.
Muchas gracias.
Por tu charla. Gracias en nuestra
for
sesión.
your attention in this evening.
Bueno, muchas gracias. Entonces, esta fue nuestra última charla de la sesión de Geometría y Física. Agradezco a todos que presentaron y que estaban en la audiencia. Y esto.